Today we are revisiting solving log equations, except they're going to be more challenging than they were first time around. So for our first example, we're going to look at solving this guy right here. If we have a single log expression in the equation, what we want to do is isolate that and then go from there depending on what that looks like. So in this case, we're going to bring over the 5. Multiply by 3. And then here, best strategy would be rewrite that exponentially. So it's 2 to the 6th power equals x minus 2. 2 to the 6th is 64. So x would be 66. All log equations have a high risk of extraneous solutions. The main thing we want to check for is this guy right here has to remain positive. Plug in 66 and it does. Now, just because this is positive doesn't guarantee it's 100% correct, but at least it's not extraneous. All right, next example here. Variation is we have multiple logs on the same side of the equals. If you have multiple logs on the same side of the equals, you always want to condense those together and then proceed from there. So the property is, if that's a plus, these two guys get multiplied. So we're looking at log of x plus 2 times x minus 1 equal to 1. And then once you hit log is equal to a number, typically your next move is going to be to rewrite that exponentially. That's understood to be base 10, so 10 to the 1st is equal to, and I'll multiply that out. So the x squared minus 1 plus 2 will be plus x minus 2. So that's going to be x squared plus x, and then that'll become a minus 12 when we bring over the 10. X plus 4, x minus 3, giving us two possible solutions of negative 4, positive 3. High risk of extraneous solutions of all log equations. We want to make sure that we check them. If you plug in a negative 4, it causes this to be negative. As soon as you find one place where we get some kind of interval violation, we know it's no good. Plug in a 3, positive, positive, it's a keeper. Emphasizing the fact that we're not throwing away that negative 4 because it's negative here. We're throwing it away based on what happens when it plugs into the original equation. All right, next example. This has a similar algebraic structure to the previous one, in the fact that we have multiple logs on the same side of the equals. Multiple logs on the same side of the equals, we want to condense them and then proceed from there. Well, if that's a subtraction, we want to divide these two things. So that's going to be log base 5 of x plus 5 over x minus 1. If after we condense, we have log is equal to number, next move typically is going to be rewrite that exponentially. That's 5 to the 2nd power equals that fraction. All right, now to solve this, I want to put that over 1 and cross multiply. So that's going to be 25 times x minus 1 is 1 times x plus 5. 25x minus 25 equals x plus 5. That over here, 24x equal to 30, x 30 over 24. So what's that? 15 over 12 divided by 3. Right, divided by 3. Something doesn't seem quite right to me. Feeling like something a little bit off. 15 divided by 12, that's 5/4. It's not what I expected to get for some reason. Let's check that on the calculator. I'm not feeling confident with that answer for some reason. So I'm going to plug it into the original problem. So math, log base, that's 5. 5 divided by 4 plus 5 minus the log base feature again. 5 divided by 4 minus 1. It does check. I don't know what I was looking at to doubt that, but that is the correct answer. All right. Next example, number 4. If we have a situation where it's log equals log, it's a single log on the left, a single log on the right, they're both the same base, we can think about this as canceling out with this, and it just leaves x squared minus 30 equal to 6. So that's going to be x squared is equal to positive 36 rather. X is equal to plus or minus 6. Well, whether you plug in a positive 6 or a negative 6, that squares out to 36. 36 minus 30, positive number, no extraneous solutions. We can keep them both. Again, emphasizing something I said earlier. Just because that's negative doesn't mean we're throwing it away. It's based on what happens when we plug it into the original equation. I believe this is up to number 5 now. We have the natural log of x plus 2 minus the natural log 4x plus 3 equal the natural log of 1 over x. Multiple logs on the same side of the equals, that's our indicator of these need to be condensed. So that's going to condense to the natural log of x plus 2 over 4x plus 3. If after we condense, we have that log is equal to log structure, as long as they are both the same base, we can think about the ln's as canceling out. Set these two things equal to each other. Cross multiply. Get this over here. Factor, and we get two possible solutions to be positive 3, negative 1. Okay, positive 3, good, 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 in terms of keeping things positive. Negative 1, good, here, causes that to be negative. As soon as we find one spot to cause that to happen, that's extraneous. Okay, number 6. We have multiple logs on the right-hand side. They need to be condensed. If that's a plus, it means these guys have to be multiplied, and I'm going to FOIL this out here. So condense and FOIL at the same step. So it'll be x squared plus 5 minus 3 is a plus 2x minus 15. We are good on the left. Now that we have log base 4 equals log base 4, single log on the left, single log on the right. You can think about those logs as canceling each other out. That cancels with that. We can bring over the minus 15. Square root both sides. And we get plus or minus 4 as our possible solutions. When we check for extraneous, the positive 4 is good, but the negative 4 is not. So our final answer is just going to be the positive 4. We have 2 more examples that need to be covered in this video. Before we get into them, we need to make an emphasis in terms of algebraic structure. This and this represent 2 different things. Here, it's the x that's being squared, and that quantity is what we're taking the log of. Here, it's the log of x first, and then that quantity gets squared. Here, the property of bringing a 2 in front is valid. That property is not valid over here. So that's an important distinction to know going into the next 2 examples. This is number 7. So, comparing this, or connecting it to what we just talked about above, we can't take this 2 and bring it in front. And we're going to treat this as a factoring problem. This has the same algebraic structure as a squared minus 7a plus 12. So it's ln of x, ln of x. 2 numbers that multiply to give us positive 12, combine to give us a negative 7, minus 4 and minus 3. ln of x minus 4 is equal to 0. ln of x is 4. X is e to the 4th. ln of x minus 3 is equal to 0. ln of x is equal to 3. X is e to the 3rd. Those are both positive numbers. Plugging in a positive here and here keeps that stuff positive. Both answers are keepers. Okay, last example for today. Similar to the one we did before, you can make sure that you're aware of this distinction. We can't use this property here. This one we're going to treat as a factoring problem. We're going to bring over that 5 log base 2 of x from the right over to the left. And then that log base 2 of x is common to both terms. So we can factor that out. Take log base 2 of x, set it equal to 0. 2 to the 0 is equal to x. X is equal to 1. That's one of our 2 solutions. Log base 2 of x minus 5 equals 0. Log base 2 of x is equal to 5. X is 2 to the 5th, or 32. And both of those answers are keepers. Nothing extraneous with either one of those. Those are both good. And I believe that wraps that up for today. And I think I just made a big old line across the video here, and I don't know why. Apologize for that if that showed up on there.